A spontaneous process is one that occurs in a system left to itself. This spontaneous change will continue until the system reaches a state of equilibrium. Now we're going to discuss equilibrium later. At equilibrium, Q equals K. But the point is, a spontaneous process is going to continue until we reach this state of equilibrium. Most spontaneous reactions are exothermic. They release heat, but there are a few that are endothermic. They absorb heat. So some spontaneous changes that are endothermic. Ice will melt at room temperature spontaneously. Liquid ether will evaporate spontaneously, and ammonium nitrate will dissolve spontaneously. These are all endothermic. They absorb heat. Entropy and disorder. Suppose we have hydrogen gas and helium gas in two separate bulbs. They're separated. We allow those gases to mix. Well, the partial pressure goes down to 0.5 atmospheres in each bulb from the 1 atmosphere that we started with. Assuming hydrogen and helium are ideal gases, delta H and delta E are 0 since there are no intermolecular forces. But what we have done is we've reached a maximum state of disorder. This thermodynamic property that relates to the degree of disorder is called entropy, and the symbol for entropy is S. The higher the degree of randomness, the greater the entropy. So in this process, we mixed gases, the disorder increased, delta S is a positive quantity. Here's some more examples where the disorder and entropy both increase. When you melt ice, you have a solid replaced by a less structured liquid. When liquid ether molecules evaporate, the gas molecules have a large free volume in which they can move, and the entropy increases. And when ammonium nitrate is dissolved in water, you're taking a crystalline solid and you're replacing that by a mixture of ions and water molecules. So in all three of these cases, the disorder and the entropy both increase. So in general, entropy or disorder increases are expected to accompany these processes. When solids form liquids, when liquids or solids form gases, when the number of molecules of gases increase in a chemical reaction, or when the temperature is increased, because temperature affects kinetic energy, and that will increase the degree of randomness. So in these two examples, we want to predict whether each of the following processes involves an increase or decrease in entropy. Well, in part A, we're taking a solid, and we're forming 7 moles of gas total. And so my entropy, which is disorder, goes up. I'm becoming more disordered in the course of this reaction. And so delta S, if we solved for it, would be a positive value. Second example, I'm taking an aqueous solution and it's forming a solid. Well, a solid is very structured, very ordered, so the entropy decreases. I become less disordered. And delta S, if I solved for it, would be a negative value. Entropy is a state function and has a unique value in a given state. We can solve for the entropy change because it's directly proportional to Q and inversely proportional to the absolute temperature under conditions where the path of the change is reversible, which means the system and surroundings can be restored to their original state by exactly reversing the change. So let's look at a problem where we solve for delta S. What is delta S for the melting of 1 mole of ice? In a reversible process, delta S is Q over T. This is a reversible process because it's the melting of ice at 0 degrees Celsius. I can reverse that change by freezing at 0 degrees Celsius. So Q over T for delta S, we have 1 mole of ice. Q is 6.02 kilojoules per mole. Divide by the absolute temperature, which is 273.15 Kelvin. So it comes out to 0.022 kilojoules per Kelvin. Those are the units for delta S. Normally, however, delta S is written in joules per Kelvin. That's what you'll see in the back of the book. So 22 joules per Kelvin. The second law of thermodynamics states that for all spontaneous processes, all processes that will happen if the system is left to itself, produce an increase in the entropy of the universe. In equation form, the second law looks like this. Delta S of the universe, which equals delta S of the system, plus delta S of the surroundings, is greater than 0 for all spontaneous processes.